we supposed to do this?
No. I think that looks good. All right. Okay. So these problems were pretty rough, and they were supposed to be. They were supposed to be like harder problems for working power. Does everybody now have a sheet for it? All right, cool. We should be good to start then. So I figured what we'll do is we'll just go through these in this class. That's all I figured we'd do. If we get done early, then that's great. But starting off with the first problem here, we've got a student that has a mass of 80 kilograms. So we're already given a bit of information, and that can go right under our, actually just write G down for our givens. And then runs up 3 flights of stairs in 12 seconds. So now we have a time. The stairs are at an angle of 35 degrees. That gives us a theta. And then the magnitude of the student's displacement is 11.3 meters, so that's her distance. Then it says, what is the power developed by the student? So we want to know P. Now, there is a few equations that we're going to need to find power. Someone give me one of the equations. What's the starting point? What is power?
Work divided by time.
Yeah, there you go. And that would be great, but we don't have work here. That's not one of our givens.
So you need force times.
Right. So now we need the equation for work, which is force times distance times cosine theta. Now, there's one more equation that we're going to need because, as you can see, we don't have force listed up here. So what's that equation? What's the equation for force here?
Mass times acceleration.
Mass times acceleration. What is the acceleration?
Gravity?
Yeah, it's the acceleration due to gravity. That's the force that we're fighting against here. When I'm trying to climb a flight of stairs, the force that I'm fighting is gravity. So it only makes sense that we use the force due to gravity, or we use F sub G. Okay, so that's going to be another equation that we use here. So substituting should be fairly straightforward here. If I go and write our setup step, just putting all these equations together, get the power. I'll just combine one at a time here. First off, I'll just put FD cosine theta in for W. So I get FD cosine theta over T. That's a good start. But of course I need to put in force too. And it just makes things really clean and organized when you do this, and you just write all your variables out before you go plug in. You don't have to. A lot of people in high school, at least, they like to just plug in right away. That's completely fine. Generally in college, people start having a change of heart and they like writing it organized because they get more used to variables. You guys aren't necessarily super used to that yet. So I have mg next. I know that's equal to F, so I can plug that in and get exactly the equation that I need. But there is an issue with this when you go and plug it into your calculator. And the issue is that the theta that you're given here doesn't really work out. It's not the theta that you want. And so the key here, so you don't get tripped up with these kinds of problems, is going to be to draw a diagram every single time. Just draw a quick little diagram. It doesn't have to be anything crazy. So you're going up we're going up flights of stairs, so we can literally just think of this as an inclined plane. And we know the angle. We know the angle is 35 degrees. Now, remember, work is a description of what's happening. Okay, we want to know where is this thing going and what's the force that's pushing it in that direction. Okay, now the force that we're applying, let's say in the x direction, that's not helping us move vertically, because we care about how far we're moving. We care about how far we're moving, like in this direction. So what we need to do, or what, let's see, what we're trying to do, where are our two vectors? We need force and we need distance. Our force vector is moving upwards. Okay, because we're saying we're fighting against gravity, right? So we're trying to move straight upwards, at least that's what the force is that we're applying. But we want to figure out what force is going in this direction. Okay? Now, if we use the cosine of this part right now, what we're going to get is the horizontal component.
You want the vertical?
We want the vertical component. And we could use sine for that. But I don't really want to go changing formulas on you guys. So what I would rather do is I would take your force that you're using, and actually, I think I drew this wrong. Force that you're using is, oh, okay, no, it is. This is the, yeah, because you are moving upwards, and then your distance is this vector right here, right? Because you want to figure out the, you want to figure out the angle between these two vectors. You want to figure out how much of your force is going in this direction. Or you could say at the same rate, what is the amount of distance going in the direction of your force? Works the same, you want the angle between those two. And the angle between those two would actually be 55 degrees, because you know these two are complementary. Okay, so it is a little weird, but again, what the cosine theta, what that theta is the angle between these two vectors, your force and your distance. So if you know that, you pretty much have everything that you need. So if you go plug in your mass, your g, your d, your cosine theta, I want you guys to do that in your calculators real quick. And I want to make sure that everybody gets 424 watts. I want everybody to do that. And I want you to say something if you don't get that. Because there's one reason, if you don't make a little quick mistake, there's one reason why you wouldn't get 424.
What's the extended arm?
Is anybody not getting 424? Okay. Seems like we're all good. If anybody didn't get 424, it's probably because your angle is supposed to be in degrees here. Just make sure that you, when you're in your mode in your calculator, sometimes, especially from like other math classes, if you're using it for pre-calc or you're using it for calc, your calculator will be in radians. You're used to seeing like pi over 6, pi over 4, pi over 3 a lot. And if that happens, then, excuse me, then you have your entire problem thrown off. But yeah, that's the answer to the first problem. So that's problem 1 done. Problem 2. We have a child pulling a sled through the snow with a force of 45 newtons. It's applied to the rope at an angle of 30 degrees with the horizontal. So we're given a few pieces of information. That force of 45 newtons is 1. we've got an angle of 30 degrees with the horizontal. So that, why is that an at symbol? That's not how that works. All right, so it's 30 degrees with horizontal. And we're saying that the distance is 15 meters. And our unknown is what?
Work.
Work, sure. And the equation that we need for work is just FD cosine theta. So it looks pretty straightforward. We have to double check though, because it seemed pretty straightforward for our last problem.
But isn't the force being pulled applied? It's not applied. It's applied at a 30-degree angle.
Right. So here that force is being applied this way.
Yeah, instead of being applied to.
Right. And the distance that this thing's traveling in is to the right.
Yeah.
So we want to figure out the angle between these two vectors. That's this angle right here, which we know was stated. That was 30. Okay.
But you
So
need,
here-
but you need to find the force that is being applied to the distance vector, not only the.
Right. Yeah. So I think I see what you're saying, right? We want to figure out what component of this force is in the x direction.
Yeah.
Yeah. Because that force, you can break it up. You can you can break it off into its components. This force, it's got some piece of it going in the y direction. It's got some piece of it going in the x direction. And just being able to recognize that, and if you multiply this by cosine, you get the x direction. If you multiply by sine of this angle, you get in the y direction. And that changes completely if you're given this angle instead. And what you'll actually find out, I don't want to confuse you guys yet, because this is not something we're going to talk about. But if you have this angle instead, and you want to find the vertical component, now you multiply by cosine of that one. So that's why a vertical component doesn't always mean use sine. It depends on the angle you got. But I don't think we're going to be dealing with that really anytime soon. Maybe when we deal with like friction, which I will take you guys back through during lab sessions. But not today. Okay. So yeah, just plug in FD cosine theta. You should be good here. I think you should get 585. Can anybody confirm that for me?
Yeah.
Good, great. Okay, cool. So that was problem 2. Problem 3, I probably should erase the board for. Does anybody need me to does anybody not want me to erase? No, okay, good. Okay. Problem 3 is another problem that involves stairs. But this time, we've got an 80 kilogram person. Carrying a 55 Newton package up the flight of stairs. It's giving us the weight of this package. It's giving us in newtons, but that's not really a nice usable form for us. It can be, depending on how you work out the equation, but I'm sure most of you guys probably want to convert this to mass, and that is something that we talked about last time. So 55 Newton, that is going to be, that's a force, but it's kind of like, how do I put this? It's the force of gravity on the package. So that's kind of what I'll write as F sub G for right now. But we're going to use that a little bit differently in a second. Now there are 80 steps, each 12.5 centimeters high. That's just giving us the amount of vertical height. So if we want to go through and just do some dimensional analysis real quick, or I don't know if that's what you guys call it. You guys probably call it unit conversion. In college, they get really pretentious all of a sudden, and they start going, oh, well, we actually just have to use dimensional analysis. I'm like, what is that? And it's literally just unit conversion. They just decided to be pretentious all of a sudden. But I'll just do that real quick. So we have 80 steps. And this is how you know that you are doing unit conversion right. We know that it's 12.5 centimeters high. So that tells us that there's 12.5 centimeters each step. And then we have that unit of step canceling off. And then we're in centimeters, we want to get to meters. We know that there is, in 1 meter, there is 100 centimeters. No, you have centimeters canceling off, and meter is the last unit. That's just something you can do really quick. It's not horrible. It's not super fun either. I know there's something about 8 and 125 that works out really nice. So I have a feeling that this is going to be something nice. Yeah. Yep, okay. So it's 10 meters. Yeah, I think what I was thinking about was when you divide 1,000 by 8, it's 125. So there is some relationship between like 8 and 125 that I've been thinking about, but your distance here is 10 meters then. And we have that all down. We can just write that right away. And we got rid of all this gross part here. Actually, I'll keep that on the board for a second. Okay, so if we have that, we really just have to figure out what our unknown is, and that's just how much work is done. And our equation, we know that work is equal to FD cosine theta. Now, in the first problem, we were going up a flight of stairs, and we were given theta. In the third problem here, we're going up a flight of stairs, and we're not given theta. Does anybody know why that's not an issue here?
Because you're finding the force that is going up the flight of stairs, not the x on x.
Yeah, pretty kind of. I mean, like, the issue before was that here we have our, like, we're going up a flight of stairs, right?
Where you want to find the force going horizontal.
Yeah, what we're finding, what the forces that we used in the first problem, we used the force that was going upwards, just the force that you're fighting against gravity, right? So you are applying a force directly upwards, is the idea. We know what that force is. Okay, we don't necessarily know yet what the force is that you would apply in this direction. Now that's the same exact force that we're going to use here. We're going to use the force that we're using to fight against gravity. But the distance here is different than what we had in the first problem. The distance in the first problem was a distance in this direction. It was giving us the total displacement. Okay? Here it's different. And so there's no actual angle between the two vectors in this case, because the distance that we're given here is we're given vertical distance. We know how high these steps are. We know how much we have to go upwards. So now there's a 0 degree angle between these two. So we actually already know theta at 0. And that means that the cosine part is completely, it's just 1 here, it doesn't matter. Remember, I said when you're applying the force in the same direction as the distance, the cosine just ends up being, not pointless, but it ends up being 1, you don't need to worry about it. So, I thought that was a really interesting part about this problem. But, with that being known, there's not really any setup that we have to do here. The plugging in just gets a little bit difficult. Because we do have to also use that the force of gravity is equal to mg here. That's another equation that we'll have to use. I'll just probably solve right away. So, we know that the force is equal to mg. So, where am I? I'm trying to make this as organized as possible for you guys. I guess I will do a setup step. So I'd like to convert this to a mass, because the person's not just carrying themselves, they're carrying a package too. So I want to figure out what the mass is of that package. And to do that, if I know that the force of gravity on it is 55 newtons, I know how much it weighs. But if I just divide that by g, right, divide g on both sides, you solve for mass. If I divide that by g, I get my mass. So 55 newtons, the mass of the package, is 55 newtons divided by 9.81 meters per second squared. And I believe that ends up being something like 5.61 kilograms. that's a little bit we have to do to kind of set everything up here. But actually going and plugging in now, and I guess I could do a little bit more to set up, just like I could write that mg is equal to force here, but we've done that already. We know that work is equal to mg times d times cosine theta. And the mass here is the mass of the person plus the mass of the package. You gotta account for both of those here. And so you have 80 kilograms plus 5.61 kilograms. That's times g, which is 9.81 meters per second squared. And then cosine of theta, we know theta is just 0, so if you want to write cosine of 0, you can. If you want to just forget about the cosine term, you can. Doesn't really matter. And what you should end up getting when you plug in is a work of 8398 joules.
Is your distance now?
Did I not put it in? Oh, yes, thank you. You have to multiply by 10 meters. You know, just erase the cosine term because it's useless anyway. And I'll put the 10 meters in. Yeah. And fine, I'll write cosine too. There we go. Thank you. Okay. Does anybody have any questions on that? Because that one can get a little tricky. The issue is just trying to remember, like, just because you see something in newtons, yes, it is, it's a force, but that doesn't mean that it's like what you're gonna plug in for this force here, because that's not what ends up happening at all. Okay. So for number 4, we've got a force of 1800 newtons is needed to keep a piano from sliding down a 10-meter ramp. How much work is done? Can anybody tell me what the answer is right away?
0.
0. Why?
Because you're not moving any.
We're not moving. We are applying a force. We are releasing energy in a way. But that energy is not being transferred to the piano. Right? Because if it was being transferred to the piano, then the piano would be moving. It would be gaining kinetic energy. We are not transferring it to the piano, or actually, it wouldn't be necessarily gaining kinetic energy. It could also gain potential energy. Because if we move it up the ramp, not only is it, it's got kinetic energy because it's moving, but it's also gaining potential energy because as soon as you let that piano go, it's got even farther to fall now. So it's not gaining any energy if it's not moving. So we're not giving energy to the piano. Of course, you're still exerting energy, right? You're still like putting in effort. So why are we not calling it work? Well, you're not transmitting energy to, or transferring energy to the piano. You are transferring energy, I guess, to, there's different chemical reactions happening inside your body that are giving you energy. You could say that that energy is getting released as heat into the atmosphere. So you are technically doing work. But the work that we're talking about here is the work on the piano itself. So in that sense, no work is done. Okay, we're not talking about any heat energy or anything like that. The number 5 things got a little hairy. Because now we have some like rotational stuff that gets put in, some orbital mechanics. We've got a satellite in orbit. Its mass is 9.3 times 10 to the 2 kilograms. You can write it as times 10 to the 2, or you can write it as E2. Well, you probably can't write it out as E2 on the Regents. I don't know if they would care, but I don't care if you write it out as E2, just because that's what you're going to put it in your calculator as. It's just a shorthand for scientific notation. We've talked about that before. Now, the distance above the surface of the Earth is 1350 kilometers. And what we can do is convert that right away to meters. If we convert that to meters, we just got to multiply by 1,000. So we can write this as 1,350,000 meters. If you want to do that right away. Okay. So we're asking what the gravitational force is acting on the satellite. So that's our unknown. This is G. This needs to be moved over. Okay. Cool. So if we want to know the gravitational force, what equation do we use? There's a few equations. There's mg, but there's another one that we're going to use in this case. Yeah, bonds.
GM 1 times M2 divided by squared.
Yep. Okay. And the two masses here is the mass of the satellite and the mass of the Earth. Those are the two bodies that are here. Let me fix that, because now I actually have to use my reference table. So we know what G is. That's, I think, 6.67 times 10 to the negative 11, yeah. And it's got some bunch of units on it here. Meters squared over kilograms squared, I think. Yes. Mass of the satellite is 9.3 times 10 to the 2 kilograms. And then you also have your other mass of the Earth. That's on your reference table. The mass of the Earth. Where is that? Mass of the Earth, 5.98 times 10 to the 24. Okay. Now that's all got to be divided by your radius squared. And if you didn't draw a picture here, that radius might have messed you up a little bit. Okay. So we've got a satellite here. Okay, we've got the Earth. And what we're given here, the distance that we're given, is the distance to Earth's surface. But what we want to do is we want to find the distance between the two center of masses. That's exactly what we have to do when using this equation. And so we also need the radius of the Earth. We also need the distance from the surface to the center. So there's some extra distance, the radius of the Earth, that we have to add on here. And that'll give us the entire radius, or the entire distance here. The reason why you can call it a radius, I don't know if anybody, I've talked about this, I thought in lab, I don't know if I talked about it with everybody here. If you think about this thing orbiting around in a circle, right? This distance is now the radius of that circle. That's why it's R in the force of gravity equation, and not D. But if you want to think about it as D, it literally doesn't matter. I'm just giving you the reason for the change in notation. So if you add those two distances, you add that's 1.35. If something's in the millions, it's times 10 to the 6. So that's 10 to the 6 meters. We've got the radius of the Earth, which is 6.37 times 10 to the 6 meters. We know we got to square that. You got to be really careful putting that in your calculator. And if you do it right, you should get that force of 6,200 newtons. So that's part A. If anybody's having trouble with that, let me know. It's a lot to plug in. I think the important thing is, especially if you're prone to calculator mistakes, just write all the work, like write everything that you're plugging in. Write what it should look like inside of your calculator, and then you can just make sure you're not getting like a bunch of credit taken off. And yeah, okay. So here's some people typing along there, so I'll let you guys do that for a second before we move on to part B.
What's the answer?
Answer's right on your sheet, so it'll be 6,200 newtons. Not quite? Or, well, it should be around 6,200, I don't know exactly.
2, so I think it's messed up times 2 or something somewhere here.
Times 10 to 14.
Is that supposed to be 10 to 24?
You did put these 6.67 to the -11. So again, just to make this look nicer in your calculator, what it should literally look like, what you should like be writing down. You can do 6.67 e -11
That's
times 9.3 e2 times 5.98 e24, and then you do divided by, and then you'll need parentheses for this, but that's about it. 1.35 e6 plus 6.37, or yeah, 6.37 e6, and that'll get squared. And that should give you exactly what you need.
where's the E button on the calculator?
Second comma. It should say EE.
Oh.
I don't know why there's two E's. I don't actually understand yet. I need to probably look it up, figure out why E is like the shorthand for times 10 to the blank. I don't know. I've started using it and never looked back. It just makes things way nicer than writing out all the other notation. And give that a shot if you haven't already. It just saves you so much time. Better to get it wrong now than get it wrong on a quiz or a test. Is this problem being stubborn for anybody? Plugging it into the calculator? Anybody having trouble? Cool. That's fine. So, part B is asking, what distance does a satellite travel in one revolution around the Earth? So, I mean, I drew out the path, right? It's a circle. We have the radius of that circle. Right away, we can figure out what the circumference is, right? Circumference is equal to pi times d, and well, d is equal to 2r, so you know that the circumference is 2 pi r, and just plug in your radius that you already had. That's what's down in the bottom here. Down. C, sketch the satellite above, showing your f sub g, your force and your velocity vectors. Okay, that's fine. Here's an acceptable answer for that. It's going to be that you have your force of gravity coming in here. The thing's got some velocity going this way. Or the other way is fine too. And you've got your force of gravity being attracted back. So there's like a little bit of force. going back there, but it doesn't do as much to the Earth because the Earth weighs more. And then, how much work is done by gravity on the satellite during one revolution around Earth? This is a really interesting question, part D. Okay? Can anybody tell me what the answer is for part D? So the answer is 0. The reason why there's 0 work being done is the distance that you're traveling and the force, they're always perpendicular. So that force isn't causing any of your motion. Like it's not driving any of your motion, I guess. It is causing you to change direction, but that's really about it, I guess. I'm not sure if that's, I guess, the best way of explaining it. But yeah, the force of gravity isn't doing any work in orbit because it's not pulling you in the direction that you're moving. It's always trying to change your direction. That's its goal, and that's why orbits exist. Does anybody have any questions on that? If you're trying to figure out how much work something is doing right away, like that picture is going to help you so much. And then we'll either get the last 3 problems done tomorrow or we'll figure something out. But I think my goal is going to be to do maybe a few more problems on this, and then we'll do like a quiz. But it won't be tomorrow. I'm not sure if it would be Wednesday. I'm thinking Thursday. We'll see. That's, I guess, all the problems we'll do for today. We'll do the next 3 problems in the next class, and then I'll probably have another sheet for you to do. That'll be the last practice that we do before the quiz.
You think when we take the quizzes, there are gonna be questions like
No.
that set level?
No. I mean, there could be little tricks thrown in here and there, but I'm not going to give you problems that take an entire class period to do. It's going to be closer to the first worksheet that you got than the second. But I wanted you to be ready for like all the crazy stuff that can get thrown at you. That's why I've given you this sheet. If you want to try the other 3 problems for homework, you can. I'm not going to make you do that, so that probably means you won't do it. But all right, cool. You have,